I'll just do this then. Hello, everyone. I just wanted to welcome you to the tutorial. Joel Halpern is going to talk about Identifier Location Network Protocol. I'm Karen O'Donoghue with the education team. If you have any questions or comments or suggestions for future tutorials, we would welcome them. And I believe, did you get the link at the end of the slides? There's a separate slide. Perfect. We have a survey at the end. We would really like you to to fill that out. Thank you very much and enjoy your day.
Thank you all for coming. I'm Joel Halpern, presenting this material on ILNP, basically on behalf of Ran and Salim, who've been doing tons of work for quite a number of years on it. No, I don't. Thank you. We're not in a cave. And unfortunately, neither of them could make it here this time, so they asked me to present it. I'm happy to do so. I am happy to take questions during the presentation, because questions at the right time are better. If the question is too detailed or takes too long, I'll ask you to look at the backing material. There's lots of backing material that I will not be presenting today because we only have an hour. And if that doesn't work, find me during the week. I am more than happy to talk about this at whatever detail during the week, but I can only go through so much during this session. I want to really try to give you a view of what this is, why this is, and what's been done with it. So I'm presenting. Ran, he labels himself co-conspirator. He's been doing this. He basically came up with the idea based on older work from Mike Odell and other people, and then keeping on. Salim at the University of St. Andrews has done work using a whole bunch of, working with a whole bunch of his students. And they've done a lot of work over the years. This is based on the routing research group work, on the namespace research group, all sorts of work that was done in other parts of the IETF, and lots of mailing list discussions. So, background. IP address is considered harmful. Going back to, this is the most recent one, but is a paper on why the fact that IP addresses represent both location and identity, and in some cases semantics and other things, combining all those into one thing creates a mess. Makes our life much more difficult than it otherwise needs to be. Now, there's a long tradition of combining them. This is not something we suddenly did at the last minute. No, we did it in the first place. We realized it causes problems. RFC 2104, going back to 1997, identifies that identifiers should be assigned at birth, should never change, should never be reused. Now, we're going to talk about changing because with modern privacy, that never changed gets to be a little more interesting, but when you're using it within a session, you don't want it changing. If you think you're talking to one guy, you better think you're talking to one guy. Locators should describe where something is in a topology and should, in principle, change whenever the topology changes. That is a fundamental conflict in goal. And IPv4 is an interesting compromise, and IPv6 retains, at least currently, that compromise from IPv4. That's our early history on this. RFC 6115 is the output of the routing research group produced by the chairs of the research group. This is not a consensus RFC. One of the nice things about the research groups here at the IETF, well, really the IRTF, is they can produce results that aren't necessarily consensus. And this is what the chairs concluded. And this was their recommendation. I won't read it out carefully, but it's worth knowing a number of people who are not involved day-to-day with ILNP think this is useful stuff and addresses real problems. Note that, for example, Lisp, which I actually co-chair, was another effort to solve the same problems. And Lisp is really useful for a bunch of other things. It turns out not to solve internet scaling. It does some other things really well, which is why I'm continuing to work on it. But it doesn't solve the problem we set out to solve in the routing research group. So, with that, let's see what we're actually talking about. The Identifier Locator Network Protocol. And yes, that's a mouthful, which is why I always simply say ILNP. It is a set of architectural concepts and constructs and approaches and ways of thinking about it, and those are documented in RFC, and a set of specific protocol mechanisms and behaviors that realize that say, okay, if you're trying to do this degree of separation while not having to encapsulate, while not changing the way the core works, all the other things you need to have an operational system, how do you do it? And it goes through in a fair bit of detail, and there's a base protocol document, there's an ICMP document for some extensions that are needed, there's the DNS extensions document. It's done in a series of RFCs that tell you how to do the protocol after you have the architecture. So engineered for leveraging the current environment. This is not go out and replace all of the routers in the world. Never been able to figure out how to do that. So let's not. Current world. IP addresses are bound to interfaces. That's the way we do things. We understand this. And since IP addresses are about topological location, interfaces are the topological location, so it entirely makes sense for IP that they're bound that way. But that means that if you have multiple interfaces, you have separate IP addresses, which that's useful for picking which one is going to receive things or send things, but it's not too useful for saying, wait, I was talking TCP over there, I'd really like to be using it over here. Doesn't seem to work right. And there are various interesting combinations to try to solve that without making these changes. This is an underlying approach to solve it at the IP layer to give us a lot of power. And we make no claim that this is the only way to tackle any of these. There's lots of ways to slice this. So fundamental naming. In our current IP world, we name things with IP addresses. If we're lucky, applications that name things with DNS names, but after that, everything is named with IP addresses, which creates a very tight coupling, which you'll see illustrated in the next slide. We don't need to do that. Now, at the application level, what you want to do is work in terms of DNS names, and we've actually got lots of RFCs which say that, and lots of practice which says, unless there's a real specific need to get to a specific IP address, work in terms of DNS, please. It makes things work a lot better for many reasons. And yes, all of these slides, I just saw somebody taking a picture, and you're welcome to. The slides are posted on the materials page. So you don't have to, but you're certainly welcome to. Not a problem. In contrast, when you use ILNP, you have DNS names, you have node identifiers, which are what transport can work in, and that includes things like IPsec, which, yes, IPsec is bolted into IP, but really it's a transport thing. It can be TLS, it can be IPsec, it can work in terms of the node identifier, not in terms of the locator. The network works in terms of the locator, and of course, your interface works in terms of its MAC address because we have neighbor discovery, and that can do all the things it needs to do. We've in fact gotten further and further away from embedding media addresses into the lower portions of IP addresses. We still do it sometimes, but we see lots more work on privacy and other things that say, you know, maybe that's not how you want to do it. However you want to do it, we don't care. Your locator can be what it, and identifier can be what they need to be. So we're now going to talk about engineering. And on this slide, we're going to use the abbreviation ILNP v6. And I think on the rest, we just talk ILNP, but the assumption is we're talking ILNP for v6. They actually did do, as part of the early work, an RFC on how would you do this engineered for IPv4. It uses things that don't work very well on the internet, like IP options that need to be manipulated. In IPv4, it just, you can make it work, but it's not a good choice. There's not enough bits in the danged address. Don't try that. So we're going to focus on IPv6. We still use a little IP option for one thing, but it's something that's only end-to-end. It's designed so on the wire, it's just the same IPv6 we always know. The same packet format. It goes through the routers exactly the same way with the same prefix lookup that routers do. There's no specially modified routers anywhere. It just works. And whether frankly, I don't care if they're switches that are looking at it, routers, it just works with our packet handling infrastructure. Yes, there's one of the RFCs talk about interesting proxies you can make. You can add things if you need to, but fundamentally it works with the existing infrastructure all the way through. And it works with existing binaries, and you'll see it later in the presentation how that's achieved. It works with existing applications and existing binaries. I was a little surprised they managed to pull that off. I thought you'd have to do something different, but they actually got it to work. So it's really nice, and it is end-to-end. Transport protocol binds end-to-end, the behavior is end-to-end. It's the way we want things to work. So it's built around two pieces, the locator and the network identifier. They are each 64 bits. And to get ahead of ourselves for a moment, so you have the right model in your head, you put the locator in the upper part of the IP address, you put the identifier in the bottom part of the IP address, and guess what? Routing just works on the locator because that's what it's told. Hey, it's a prefix. It doesn't care. So locators are topologically significant. They are what routing will pay attention to just by its normal operations. They name subnets, network prefixes. And if you want to do /128 routing on a part of your network, then that part is, for this purpose, the thing named by the locator. We don't really care how you structure it, whether it's really a bridged space or a hybrid bridge router. It's the 64 bits gets you to the edge, and you can deliver it from there. The node identifier is stable and not topologically significant. That's the whole point of it. You get both of them from DNS. You can use something else if you want, and we'll get to that too, but you get them both and then you use them. And that means you can have multiple locators associated with the same communication session, because the end-to-end session is bound to the network identifier. You have a question, please.
And both of those are globally unique?
The locators are not globally unique. All of the devices on the same subnet will be using the same locator. The locators are topological with whatever structure topology. Node identifiers are globally unique. There is actually a mechanism in the protocol so that if two things somehow manage to collide on their identifier, things will still work, but from all the analysis we've done, they will generally be globally unique, and it's much easier to work with if you achieve global uniqueness. But in fact, if somehow accidentally there's a collision, everything still works. And there's details on that in the backing material if you want to see how. The point is that also it names the node. It does not name the interface. You pull interfaces out, put them in, turn them on, turn them off. The identifier stays the same. It's in a lot of uses here at the IETF, we have to create what are called loopback addresses to create a name that is stable when you have to add and subtract. Well, no, this is not an interface name, so we don't have to make up an interface for it to be attached to. And the whole key here is the upper layer protocols, TCP, UDP, QUIC, whatever you're running, TLS, operate in terms of the node identifier. They ignore the upper 64 bits. And getting that to be backwards compatible so that you can talk to existing nodes who don't do this does take a little work, but that's in there too. So this is one of the things that was kept in mind in design was deployability. You don't have to ensure that everybody is cut over the first day. We don't do flag dates. So nodes that speak ILMP can still talk to existing nodes, and we'll still do the right checksums so that everybody does things right. You won't get the ILMP advantages for those sessions. Well, that's okay. That's a trade-off because not everything gets updated at the same time. So the locator 64 is named subnets. You can change your location during the session. There are multiple mechanisms to do this. There's actually an update mechanism that is exchanged between nodes so that if you are moving, if you know you're going to move, you can tell your partner. If you have multiple interfaces and you add a new one, you can tell your communicating partner about the new one. So classic soft handoffs run really efficiently, as you'll see in the later statistics. Worst case, go do a DNS update. If the guy can't find you, he goes and rechecks DNS and gets through. And one of the experiments they did early on in making all this, and the reason I talk about DNS, said, what if we cause the leaf node DNS entries to have a lifetime of 1 second? Does anything break? Nope. They actually took the entire university, that's a substantial thing, and cut everything so that the leaves, not the rest of the infrastructure, had 1 second lifetimes, and everything just worked, and the load didn't even go up much. It doesn't even cause significant, I'm sure there was some increase. I don't have the statistics for that experiment handy, but it was very small. So you really can use DNS as the backup here. It does work as a backup rendezvous mechanism in addition to an initial discovery. So we have communications mechanisms to maintain and update locations, and we have DNS as the fallback. And of course, you can use multiple ones. That's, in fact, part of the point here is you can use multiple locators simultaneously, however many you want, with however many partners you want, and it just works. Nothing, no complications, it just works. NIDs, in contrast, are node names. They are not interfaces. So you can have multiple NIDs. Now, why do you want them? Either for privacy, or if you have different sets of functionality and want to be viewed differently, or you're doing virtual machine things and want them to be viewed as separate entities. There are lots of different cases where machines really want to be seen as distinct. A machine really would like to be seen as having distinct identities. Fine. That means you won't get session handoff between them, but that's, you've chosen not to. And it works just fine. And you can then create DNS entries. No, you don't, if you're the initiating end of a communication, you don't need to create DNS entries if nobody's ever going to connect to you. You can just connect to other people, provide them things, and when you change your connectivity, send them the updates over the new connectivity even. Everything keeps working. So we can use DNS, but we don't require any additional DNS information that was not already in the system, and we get these global identifiers. They can be assigned statically, and so, for example, if you have a server that you want well-known in your environment, or well-known globally, you assign it a static identifier and everybody's happy. They can be assigned by any dynamic means you like for whatever reasons you like. The rule is if you want to maintain a TCP connection, don't throw away that identifier while you're in the middle of the session. Please.
Thank you. 2 questions. First of all, are these NIDs? What's the problem there with you have collisions? How is that going to be resolved? If the names are going to be allocated, these NIDs are potentially being generated dynamically. What about the possibility of 2 devices clashing by hashing to the same NID? How's that resolved?
So 2 things to keep in mind. First, it turns out that if you randomly generate these things, the odds of getting 2 of them together are really tiny. So globally, yeah. It seems to be good to be the case that we don't expect to. Now, we do have to think about that because usually it's square root 4 billion. We are now talking about more than 4 billion nodes. So when we did the analysis, it was definitely the case. Now it may not be the case. And in particular, when we get to 50 billion. So that may not be. The other thing that happens, and the real answer to your question, when you establish communication with someone, you include what's called a nonce.
Okay.
And if you have the same ID but a different nonce than someone else, you will be considered a separate session. So your nonce becomes an additional set of random bits that qualify and distinguish your global ID from anybody else's. and you maintain your nonce when you move. So, and each side sends a nonce to the other. And so, and any of the updates carry the nonce. The nonce was originally invented to provide security from off-path attackers. Because we have location updates, if you didn't have something in the on-path communication, an off-path attacker could just generate messages that said, this guy moved, here's his new locator. Well, that would be really bad. So the nonce protects you against off-path attackers. It also qualifies the session. So as a result, that provides extra uniqueness in case of connection. And the point that was just made, we probably need to emphasize that more in future work, because with the current scale of the world, no, randomly generated things are not going to be globally unique, and you're correct.
Okay, so these things with the NIDs, users envisage these are going to end up in the DNS.
Yeah, so when you create one, if you want to be reachable, you're going to create a DNS entry with your name and your L64s, however many you have, and your NID. And there's a specific record that is supported by most DNS servers out there already. You just, nobody knows it, but it's actually supported. And we'll come back to that.
Well, I've got two questions about that particular issue. First of all is, how do you solve the authentication problem of actually updating the DNS? How can the DNS administrator trust you to update the information and do it correctly? Secondly, and perhaps more importantly, is when a device leaves the network or somehow detaches itself or switches itself off, how do we make sure that that crap that's in the DNS gets removed?
Okay, I'll get to the first question a little later.
Okay.
But the second question, we don't care. And
If I'm running a DNS server, I will care, because I'm going to have all this stuff.
No, whoever's naming tree you're in may care. And there are all sorts of ways. If you do them with short lifetimes, for example, and refresh them, if you're using dynamic, the preferred path is dynamic DNS, which has authentication for entries. If you've created the entry with dynamic DNS, and then you have lifetimes and refreshes, and things will go away. They won't hang around for days after you're done. And if there's an entry that is wrong at the moment because you're not there, there's no pain from that, because you're going to be back if you're really part of the system. So yes, somebody trying to reach you may be unable to if you're literally unreachable, but that's okay.
Well, it may be okay in terms of the connection being established and all that kind of stuff going on. I'm thinking more from the perspective of running a DNS server, having all this extra junk lying around my DNS database.
Well, if it's dynamic, that's why I said, if you use dynamic DNS, there's already provision for cleaning up.
Yeah, but only if the device chooses to remove its entry when it decides it's going away.
Well, no, there's also provision in dynamic DNS for the entries to go away if they're not maintained. Dynamic DNS has lifetimes in it. And you make them much, much shorter than you do classic server entries. You don't create entries with lifetimes on the order of 30 days. That would be silly. The point is, this is, we have the tools for solving this. If the spec doesn't currently say that, it's easy. The point is, you're correct. We should make sure they don't live forever to clutter things up. But presumably, if somebody's got dynamic DNS, remember, this is way down at the leaf. It's not like .com has to maintain these. .com doesn't know anything about these. Ericsson.com probably doesn't even know anything about these. It's probably further down so that you can manage them in appropriate servers and distribute the load of maintaining the information. But that's the point is DNS, I don't want to go on too long, and there is some backing material on some of this. You may be right that we want to put in more advice about how to use dynamic DNS. That would be perfectly reasonable.
Okay, I'm concerned about the scaling issues, but I'm going to shut up now because there are people on the line.
Hi, if NIDs remain 64 bits, there will be lots of collisions. And I think you explained a little while ago, that's going to be okay.
Yep.
And then you mentioned the nonce mechanism, which I'm actually not familiar with the details. But I believe if there's a collision, but they never are exposed to each other, and nobody who's in touch with either of them is ever exposed to them, then who cares?
Exactly.
There's no problem. The problem is if two people wind up with the same, if I wind up with an idea that I'm using to contact some large service, and somebody else unfortunately generates the same NID and tries to contact that same large service, I think you told me there's a nonce and it's going to be different. does it just all work? We can both communicate with that
As far
service,
as I
even though
can
we
tell.
both have the
Yes.
same NID? Okay, so the nonce will be included in any message that
We
says, hey, I
probably
can
need
move
to
it through
put,
here.
start making a default to include more information about why it just works. Because as you say, collisions are going to become more common with the size of the world we're living in.
If the two of us with the same NID wind up on the same subnet because we both came to the IETF meeting.
Then bad things would happen.
Okay,
But-
that's what I thought the answers would be. I just wanted to see if I was thinking the same things you were.
Yep.
Okay, it might be nice to make the NIDs.
We don't
Twice
have
as
enough
wide.
bits to make them any bigger.
Well, maybe without changing other things.
Yeah, and Dino, go ahead.
Joel, it might be helpful to make it more clear that to get the nonce to be part of the network ID, you need to communicate with each other. But how do you do that
Well,
if you have a duplicate?
No, it
Is there a
doesn't. Turns out-
catch-22?
It's later in the thing, I think, and it's not. It's in the backing slides that the NID is sent, that the nonce is sent in the initial communication. In fact, the way we detect that we're talking, that when I talk about backwards compatibility, you send the nonce. If the other guy is not speaking ILNP, he sends you back an error saying, what the heck are you doing? And you go, oh, you're just doing classic IP. I won't do ILNP. But if he does speak ILNP, he understands the nonce. He has the nonce from the very beginning. So there's no difficulty in qualifying. Like, well, wait, is this an initial request from somebody new, or is this from, no, you can tell the difference right up front. So the point about the binding is illustrated here. Classically, everything in our protocol space is bound to the IP address. There are a few protocols which use DNS names with retry and other things to try to loosen this coupling right here, but very few. Whereas here, yeah, the application is tied to the NID, but it's not tied to the IP address, to the locator. So if you move, or if you have multiple locations, or if you add locations, things up here just keep working. Just naturally. Yes, the assumption we're making is there is an enhancement in the TCP stack in the ILNP hosts. There are what, 5 stacks that need to be updated in the world to support this? It's now tractable. Back when I was doing networking in the first place and supporting 60 OSs for my communication software, putting an upgrade in a host stack was challenging. But there aren't 60 different operating systems. Yeah, there are a lot of variants, but they use the same kernel code. They use the same TCP stacks. Well, yes, you'll see. That's so key in. So now we get how did we engineer this? So there's ongoing research and implementation. RFC is 6740 through 6748. There is an open source prototype that's been done by St. Andrews. There's support on commercial DNS. We'll come back to that. And we talked about RFC 6115. Their estimate is that we've been doing this for 14 years. It's had a lot of examination. So here's the picture of how we encode it. We put the locators in the upper part of the IPv6 address and the NIDs in the lower part. And then we simply tell routing, as we already do, how big its prefixes are. That's the way routing works. It doesn't try to, once upon a time, we had IP addresses where the routers would look at the IP address and guess the prefix length from them. We called it classical addressing. I built forwarding tables using it. There's a good reason we don't do that anymore. Turns out not doing that also makes this kind of thing much, much simpler. It falls out for free from the other work. Name resolution is DNS. That's supported by bind, by not DNS, and by NSD. Already, the bind one, at least I know, has been in for many years. And went and talked to them, and they said, yeah, we could do that. And they did it. It's really not hard. You can do etc. host entries if you want. You can also use some other mapping protocol if you need to. I mean, we've looked at what you would do in mobile networks. And some of the way things get resolved in mobile environments uses other mapping systems. Okay, that's okay too. You teach that mapping system to understand about this combination, you get all the benefits. And well-behaved applications work over with sockets, and you can do, as I already said, if there's an application-specific naming protocol for whatever reason, some of our applications have them, you can teach that. I can't say it's free. You do have to enhance it, but we can deal with it. So the resulting thing is 128 bits. So anything that handles IPv6 just sees an IPv6 address. It doesn't need to know anything is different. There are, for routers, when you're using ILNP between the ends, there is not even any recommended modifications of behavior. It just works. It's not like, well, maybe it'll work. No, it works. Neighbor discovery works. So again, you asked about what happens if you collide on the same subnet. Well, we already have mechanisms to discover that, and it will report it. So neighbor discovery, neighbor solicitation, all just works. We don't have to change any of those rules. In system OS and kernel, we have to change the IPv6 stack a little bit, yeah. We have a new ICMP message. We have to do some binding information so that you can tell, okay, which locator identifier pairs am I using for this communication so that the IP stack can know what to fill into the packet, because the transport is just working on the NID, so obviously IP has to fill in the locators, extra binding information. The transport level code has to be changed because the transport checksum is now calculated on just the NID. That's how we get the ability to change locators. The TCP checksum, the UDP checksum, is calculated using the NID, but not the locator. So from the point of view of TCP, when it gets a bunch of different packets with different locators in the same NID and confirmed by the nonce to belong to the same session, then you can just use the checksum on that. And so it doesn't have to go, how do I fix it up for these different ones? It doesn't know anything. It just runs the checksum on the NID and everything else it checksums. So that's the important change to the TCP stack. So there's changes to the IP stack and changes to the TCP stack. They both have proved pretty small. The binding one took a little more work to figure out how to do, but they've done it. The TCP is, for obvious reasons, a very easy change, just conditioned on being told by the IP stack that this is an ILNP session. And you do have to be careful at startup because you got to calculate a checksum on the SYN, and the SYN is going to be sent assuming it's ILNP, and if it comes back that you need to use regular, you need to go back to the default checksum. It's those kinds of things that make it a little interesting, but they've all been worked out. And the IPv6 binaries just work. And you'll see why and how. The basic trick is you let DNS give it back something without any locators, and the app doesn't know anything's going on. Now, you can, and we'd like in the future to expose ILNP to the applications for those things that want to take advantage of it. So we get no need for NATs, but as long as the NAT just messes with the upper 64 bits, we also don't care if you did a NAT. Now this checksum preserving identifier changing NATs, that's a different beastie, but classically, if you want to change the locators from the ones that you use internally to ones you use externally, go ahead, it'll just work. No special tunnels, so that, like the ILA guys complain about Lisp, that it adds an end caps. Well, I'm not sure that's a big deal, but since people think it's a big deal, I want to point out there ain't no end caps here. Your decision whether that matters for your use case. and no proxies. No need for any proxies for anything. No enhancements, no changes to the routing behaviors, no special routers, just does its thing. And you get mobility, you get a whole lot of features. Go ahead, question, please.
Oh, yeah, this nonce seems really critical to a lot of functionality. How is that passed in the and where is it passed in the clear in the packet or where is
It's in the clear because if somebody corrupts it, well, I mean, if somebody can drop packets anyway. If they're on path, they can do all sorts of things. Fundamental premise on security is if you want to protect against on-path attackers, use IPsec. Protected with the NID, not bound to the NID, not to the locator, but use IPsec. So we're worried about, for real security, use real security. We're not going to pretend that ILMP by itself gives you real security. However, it does give you protection against off-path attackers. Since they can't guess your nonce, even if they know everything else, they can't do that. So that's the fundamental security distinction we're making here, is between on-path and off-path attackers. And where is it put? In a destination option. Because it's only needed by the destination, so it's an IPv6 destination option. That is actually marked as generate an error if you don't understand this, so that we can get interoperability.
Okay, yeah, I don't want to get into the whole extension header controversy.
But that's why it's
yeah.
specifically a destination option, so that it doesn't get in, it's completely ignored by the routers.
Yeah, sure. Okay.
And there are those who argue that even that's not doable, but if that's not doable, we've got a whole lot of other problems because we've got an awful lot of work here that assumes we can do some level of extension on the IP header. But that's not my problem for today's discussion. We can discuss that in another working group. So, as one example, mobility. Now, we're doing it a long time, great. So, just using the standard behaviors, they've actually measured the difference between hard handoff, soft handoff, ILMP handoff, and classic mobility. Look, did you have a question? No, you're just looking for a seat. Okay, welcome. This was published, I can't tell, in AIM Tech 2016, and there's the DOI because academics use DOIs. We use RFCs, they use DOIs. Okay, that's why RFCs also have DOIs, so academics can use them. The testbed used iPerf2 to check things, because that's one of the standard things people use to measure things. Used Linux 3.9 with Cubic, and used unmodified IPv6 routers. You'll see a diagram in a moment. And as I said, in-kernel modifications for the TCP to use NIDs, the IP level changes for binding and the locator update processing so you can move. That has to be part of the IP stack, and mobile, and to actually have mobility. In order to be able to compare different cases, they also put a delay emulator into the test setup and tuned it differently for different cases to see if that mattered. So the point is, this was their test setup, one correspondent node, and a mobile node moving between two locations with the option for putting emulated WAN delay in either the source or the destination side. So they could make sure, does this work the same, better, or worse than existing mobility mechanisms in these two cases? So what they compared, since it's an IETF protocol thing, was mobile IPv6. Because if you wanted to compare cellular mobility, you'd need a lot more infrastructure. Costs a ton, which is unfortunate, but that's the way it is. So they compared mobile IPv6 with the with ILMP, and they did both ILMP with both hard and soft handoff. And you can see here that the first thing you notice is ILMP is far more predictable. Very stable, very tight error bars on their observations. In fact, you have to hunt to find some of these because with soft handoff, the behavior is so good it actually disappears into the axis. Because in terms of loss, whether you're using the WAN emulation or not, when you're doing soft handoff, you get negligible loss. It just doesn't happen because you're just able to use both things during the soft handoff and it works. But even with soft handoffs, MIP v6, even when the LAN-to-LAN case experiences measurable loss. Now you can decide whether the amount shown here is significant or not. I'm not going to argue about that, but it was certainly measurably different. And in the hard handoff case, ILMP was no worse. And dang it, come on, there. Retransmissions, again, there was more retransmission. It turns out that ILMP sometimes would retransmit even when it didn't need to due to the handoff behavior. So there was somewhat more retransmission. Interestingly, when it had enough latency at both sides, it actually could figure out what was going on and not waste its time retransmitting. But as you can see, it works well in all cases and really well even in the handoff case. So ILNP was better, the same or better. And the point is, this is running code. This is not, this is Linux code, it's open source. Yeah, we had to do the modifications, but we did it. It works. It runs. And there have been a lot of other tests. They've been running this various things in the test bed for quite some time. So they like to describe it as addressing without addresses. The point being, we use the term address as the overloaded term for a thing which is both a specific identified communicating party and at a specific place in the topology. This separates them. We have identifiers, we have locators. This is not the only protocol to separate them by any means. There are a number of other alternatives. In fact, it can be argued even that mobile IP separates them because it creates the base, the address and the co-located and the care of address, which is the topological location. And with MIP6, you have triangle elimination. That's what they were talking about was, what did you do route optimization to try to make things work better? Turns out it didn't help much for this problem. It makes other problems go away for mobile IPv6, but it doesn't solve the actual handoff problem for obvious reasons. And so it gives us much cleaner way to bind to higher levels of the architecture without coupling to topology. It's really nice to keep us uncoupled from the topology. There are those who say it's radical. I'm actually inclined to say it's actually a nice, simple philosophical step, but that's very much in the eyes of the beholder. But it's clean engineering. Obviously, there's somebody waiting with a question. Please.
Hi, Stu Card. I'm from
Tip that mic up. It'll be easier for you.
Good. Hi, Stu Card. I'm from Critical Technologies, and I'm a newcomer. It's my first IETF question.
Welcome.
You talked about various M's like multi-homing, but you left out one of the M's, multicast. Is there an interaction?
There is actually work on how to use ILNP with multicast. Ran used to actually work very hard on multicast stuff. He did one of the first IPv6 multicast implementations back when. But mostly, as a transmitter, you could use ILNP so that if you changed your location, you wouldn't break the sessions. But since the multicast trees are tied to locations, so they get good distribution effects, we aren't claiming much benefit in the multicast space. There are ways to use it, but what it's really useful for is if you want to have unicast communications tied to the multicast, you can have the unicast still do things. So if receivers are moving, They get the multicast from there, but their unicast feedback, which you want to tie to your older state about them, you still have. So there are ways to leverage the combination, but mostly we're not trying to focus on multicast. But it's a absolutely fair question. And the real key for me is the no network upgrade. This just uses the infrastructure we have. And I have lots of additional slides if there are, but we've got 15 minutes, so come up and ask questions.
So talk about deployment. How far has it gotten, and what's the downside for anybody deploying this? Why isn't it just out there and being used all over the place?
It's not being used. It is not deployed. I wish it were, but it's not out there. The reason seems to be one of a couple of things. And now I'm very much, fairness to everybody here, I'm guessing. We don't have any data on why not. We have the anecdotal stories from discussions with different people. Part of it is that some folks consider that maybe changing the host stack is actually a big deal. And the different host stack vendors, therefore each vendors is generously, the host stack builders are sort of all waiting for somebody else to decide to do it. And they've all said, you know, we could do this, but why should we put it in until somebody else is putting it in? So it's just, and the IETF, these things are RFCs, but be very clear, they are not standards. These are informational RFCs. The IETF has chosen not to pick this as the preferred approach. I'd love to see us get on this, see if there's any fixes needed, like putting more emphasis on the nonces and other things, and say, this is a standard pattern that you should be looking at, but for now it's not. And well, one could observe that that may say something about the fact that people do know the difference between standards and non-standards. Dino.
Did St. Andrews do any testing with respect to ILM? So can you get the ILNP benefits, the mobility benefits, when the server, the other side that's not moving, the correspondent node, is IPv6, not ILNP enabled? Were they able to?
They haven't done any work on that.
Okay.
I know other people who have done some work on that, and there are ways, but it is certainly more complicated to enable that.
Because I'm wondering, if you upgrade all the mobile operating systems to ILNP, but not all the server systems, do you get benefits?
Yeah, that's one I have looked at, but it's certainly more complicated. I would like to say, hey, you get them all, but no, it's not that simple. There are some more interesting, one of the RFCs is more interesting deployments, and this falls into the even more interesting deployments. But there's actually analysis on the server end on how this can be used for data centers in ways that are highly beneficial.
In terms of deployment, am I misunderstanding, or it would seem like you do kind of have to do everything together, right? I mean, if the checksum isn't over the entire address and you're going from one stack to the other, you know what I'm saying? It's like, yeah, kind of both
Here's the survey
sides.
for everybody. Sorry to interrupt you. I just wanted to, there's the survey. But now, yes, so the key is the TCP initially computes the checksum over just the NID, does its ILNP thing, sends the destination option. The other guy doesn't speak ILNP. Get back an error, recompute the checksum before you resend anything.
I see, you have a back off.
Yeah, but it's very, very fast. It's one round trip. It does introduce one round trip of latency relative to for a communication with existing hosts. And that may be one of the reasons some people didn't like it. It does introduce that latency. And Quick is trying to move to 0 round trips, not even one. That is, I don't know any way to change these behaviors that doesn't get.
Yeah, I jumped up to ask you if it added a round trip, and
It does.
you answered my question before I got to the microphone. But that's a really big deal these days. And I think that may be, I'm just guessing now, but I think that may be one big disincentive to be the first one to
It's
go
sort of,
there.
once it's widespread, that's irrelevant, but in the transition, it may be an issue.
You don't want to be the one who's paying the extra round trip. Well,
Mhm.
when most of, that's a guess on my part, but it
Now,
seems like.
one good thing, there is one other thing that you can do, which is if the connecting host supports ILNP, which is what I was hypothesizing, and the server doesn't, one of the choices you can make is to say, I will look for the DNS records. If I do not find I-64 and L-64 records, then I just won't bother trying to do ILNP. And so I can have a heuristic which, particularly for early deployment, will let you avoid the one extra round trip. Sorry, I didn't think about that when I was first responding, but one of the common heuristics, and it's not mandated, and this is why there's robust interoperability. If you do a DNS lookup and ask for an I-64 record, if it isn't there, you will be told by the DNS server, because DNS supports this stuff, it ain't there. And at that point, you can say, I can reasonably guess it's not there. And since it's not critical to me, I'll just use normal. If it's really important, if I really want to get it anyway, I might try anyway to see if for some reason he supports ILNP without a DNS entry. So there's multiple choices in behavior, but we can therefore cut out the extra round trip in many cases.
I was going to say another way to get around the round trip problem is you could use the trick in ILA where there's a well-known locator. And then if you did that, you would only have to change the stacks to get a new network layer, not a transport layer modification. You still have to change the stack. But if you do that, you might as well just use ILA. But then people say, I may not like the ILA control plane and I like the control plane of ILNP. So pick and choose your poison or your positive.
But I think the right answer is to use the DNS-based heuristic. And for most cases. Now, the interesting thing is if you're using SIP and it's giving you IP addresses rather than DNS names, then you might want to use the ILNP for the first connection to see if you can use ILNP, because being able to move while talking is a really important feature.
I hope you didn't just move the extra round trip from the connect to the DNS.
No, you've got to do a DNS lookup anyway.
And you can do you can get all the records you're interested in one,
Yeah,
and it'll all fit in the packet.
They will all fit in the packet. They did an analysis of how many it would have to be for it to be a problem, and the answer is they'll fit for most purposes. Obviously, you start putting DNSSEC signatures on, things get much harder, but that's a whole different issue.
Did they do any analysis if an ILNP node's on a high-speed train and you're changing locators really quickly, how quick you can update the DNS?
There's two issues if you're on a high-speed train. First off, you're generally the connector, in which case you use the update mechanism, not the DNS mechanism. And so with your correspondence, you can update it easily, fast enough, more than one round trip. It's not a problem. Now, and there is provision for both moving in the design as long as it's soft handoffs. And usually even, look, 1 second is a fair distance on a high-speed train, but it's not actually that, it's actually a long time in terms of network communication time. So in terms of communicating parties, keeping the updates going is quite easy. In terms of DNS updates, obviously, if you're getting a new locator every 10 seconds, don't be stupid. Don't send a DNS update every 10 seconds. Mostly you're connecting out. You don't need to keep new parties connecting in. If you think you need it, send it. Every once in a while, send it. You don't mess with your DNS server. You've got a relationship with him. And these are heuristics which can be nicely tuned once we get some real-world experience, but we think they'll work reasonably well. Next question.
Hi, just a couple of comments. I was thinking about this in relationship to multipath TCP, which in many ways is kind of similar to this.
It's related, absolutely.
Certainly related in, so multipath TCP took the decision that you kind of have a split identifier and locator. From point of view of an application, you continue to use your existing TCP address as the application identifier, and you have then network locators, if you like, as IP addresses underneath. Many you've got. So it's kind of very, very similar to this. So I'm trying to think firstly from motivation for why people would deploy ILNP. What are you, if you want mobility, the sort of mobility that multipath TCP gives you, what would be the motivation for somebody to then use, say, right, I want ILNP to get further benefits? What further benefits would you get? That's the first kind of.
Okay, so there's some backing slides that you can look at later. The basic idea is this is a common mechanism which can be used by multiple upper layers. And then the upper layers can add extra value if they are aware of issues with multiple paths. So we could do some things so that, for example, multipath TCP is good at keeping track of different congestion behaviors across different communications. With a little cleverness, you could we believe, and we've tried to talk with some of you folks and it hasn't worked well, but I think it would be worth having the exploration, that if multipath TCP was aware of ILNP state, you could do some really nice congestion separation so as to get the congestion behaviors that MPTCP very nicely adds, which TCP, after all, if it's something else, it'll be some different congestion, over the multiple mechanisms that ILNP makes available, multiple communications paths that ILNP makes available. So it'll simplify the use of multipath TCP. You don't have to send new SINs or anything, but you can still keep track of congestion behavior separately, and so get a lot of the optimizations you guys have worked out in conjunction with ILNP. So we think that there's actually some good synergy between the two.
And I'll talk more to you about that later if possible. So my other thought was, which has now gone out of my head. It might come back.
Sit down and as I said, I'm more than happy. I'll be here all week. I
know what it was. So in terms of the sort of deployability, so multipath TCP is in all a kind of Apple OS, so that's been very successful. But in terms of the Linux kernel, so you can download it, but getting in the mainline kernel has proved to be surprisingly difficult. So I wondered if there would be some lessons, mutual lessons to learn there.
I think you guys
there's a talk that Christoph's doing later in the week about how hard can it be to get MPTCP in Linux mainline kernel. So there may be some stuff in that.
You guys need to talk to Salim. He's been working that, and I think he could benefit. His work could definitely benefit from talking to you, and because you've each come at it from different ends, there's probably insights both, but he could definitely use the insights you guys have had.
Right.
And he's not far from you. St. Andrews is just on the other side from Edinburgh up in Scotland. So, okay. No, I got through all the slides I wanted. I have hordes of backup, which were primarily there for, you guys can go through at your own pace, look at them, and then find me and ask questions. And your comments about the nonce, I will be relaying to Salim and Rand because I think it's very important. We've pretended you can leave the nonce out of some things, and you can because the locator also qualifies things once you have an ongoing session, but I think we need to do some more exploration and explanation of the behaviors.
Yeah,
I think it all works, but it's not well explained.
I have been almost a fan of ILNP from its very earliest days, and I think what's different now, though I haven't paid attention to it for many years, I think the story now is much better because you don't have to explain how it works over IPv4. And I realized, sounds much better now than it did last time I was trying to understand.
Doing it over v4 was,
yeah.
no, don't go there.
The remaining part that I'm concerned about is 64 bits enough? And I was sitting here trying to think about, if this is where the future was going to go, should IPv6 have been 192 bits instead of 128?
Well,
Because
It should have been variable length, but that's a different.
I remember that. I remember those
I'm
arguments.
good on blasphemy.
But so I'm trying to imagine a future if we decide that this is good and it catches on and we get the changes into the 5 OS kernels that are needed and goodness comes from ILNP. And then we go into the future. Is because we've done that, are we going to at some point have to do something that's wider than 128 bits?
I hope not.
That may be 50 years from now.
Well, okay, 50 years from now, I would be willing to bet 50 years from now, we will be doing something different anyway.
Than IPv6 anyway.
Yeah. And one would hope it will learn the lessons from PIP and ILNP and Lisp and all the other things we've done when we actually do the next thing in 30 or 40 years. But I won't be here. That's longer than my expected time here.
Yeah, maybe then probably mine too. But I think one of the things that was very appealing about IPv6 was it was obviously future-proof. It can last for a very long time. But this changes my perception of IPv6 if ILNP were to become popular in that same sense. And the 64 bits doesn't quite feel big enough for me because I can imagine there would be people that had NIDs who happened to go to the same conference and wound up on the same.
Well,
So let me change.
That should usually use dynamic NIDs.
Yeah,
and therefore that won't be a problem. You can get another one.
Well, that might be the thing. So it would be a testing I would really like to see is deliberately have the duplicate NIDs and test everything that happens when you have duplicate NIDs and all the
Send an
different
email
scenarios.
to them. I will take care of raising that primary issue, but that detail I'll leave to you.
Okay.
That Salim and Rand both like hearing from folks with interesting ideas on the thing. So,
Yeah.
and Salim has grad students who need to run tests because they got to do things. Go ahead.
So I'm guessing that you're probably more familiar with HIP than I am with ILNP. So as someone who has been successfully using HIP, I wonder if you could give me the short case for why I might wish to migrate from HIP to ILNP.
In spite of working with the guys who worked with Bob Moskowitz on inventing HIP, I don't know of any significant deployment of HIP either. And the HIP infrastructure, because of the big problem with HIP, as far as I know, and the only thing that's ever worried me about it, is that it requires a new infrastructure. It doesn't just leverage DNS. And that creates its own set of complications. Now, some of the newer work on HIP may make it more attractive for this. I've been reading some of the recent ones, and I haven't done a comparison. I am familiar with HIP. I like it, but I haven't done the detailed comparison. But he ran into the same problems of being unable to get adoption. I probably shouldn't. The reason is that while I have preferences, that gets into controversies about how ILA works and whether the trade-offs in using routers are the right trade-offs and whether doing address rewriting on the fly is the right way to make things work. And while I have opinions, these are issues on which reasonable people can and do differ, and I want to be fair to those. They aren't here to rebut, so I don't think it's fair for me to go into details about that.
I have two questions. One, I've just been trying to think about how happy eyeballs would work in this situation. It would seem like it would would you have to go, if you didn't have the V6 path, you'd have to get a V4, and then would you also have to redo the TCP or no?
No, look, TCP over V4 does a separate checksum than TCP over V6 already.
Yeah,
So happy eyeballs V4 versus V6 would work exactly the same way.
sure, okay.
And if you get ILNP, if you get INL records in your DNS lookup, then on your V6 side you use ILNP, and on your V4 side you use V4 because That's what you do on V4, and
Yeah.
whatever works, works. So happy eyeballs should be just fine.
Yeah, no problem. So, and then what if you wanted to use, what if you did want like two different addresses for two different interfaces? Like if you were dual, multi-homed or whatever.
Well, if you're multi-homed, you have two locators because otherwise traffic can't be routed to both of them. I mean, you don't assign the same prefix to, there are people who try to work it by assigning the same prefix to two places, and really strange things happen.
Yeah.
Sometimes it does the right thing, and frankly, if it works for you, you can do that. It'll work with ILNP. ILNP won't care. It's just not usually a good idea.
So you'd have two different locator IDs
You
and
have
the
two
same
different
NID.
locators and the
And
same identifier.
NID.
Yeah,
Yeah.
works just great. And we are now over time, and since I'm supposed to be in another room very shortly, I thank you all for your attendance and your questions. Thank you.